Hey guys, Mr. L back at you with another video, and in this video we're going to cover the periodic table, how it's organized and structured, as well as how we use these symbols to come up with chemical formulas, the difference between an empirical and a molecular formula, as well as how to name compounds using the molecular, the ionic, organic, and acid naming. So let's get into this video. So to start off this video, let's look at this thing, the periodic table. The first periodic table was constructed by a Russian chemist named Dmitry Mendeleev. He organized his table based on increasing atomic masses, and in a later video we're going to talk about the American guy who reorganized this, but it's reorganized now by increasing atomic number, which is the number on each one of these little squares here. The atomic number denotes the number of protons. So if we're to zoom in on one of these little squares here, we could see the top value is number of protons, that's the atomic number. Below that is going to be a symbol, a chemical symbol, which we talked about last video. This is going to be a 1 or 2 letter designation based on whether it's a Latin name, Greek name, location, but it's going to be some 1 or 2 letter designation that tells us something about what this element is. At the bottom of each one of these squares, we're going to have the average atomic mass of each of these elements. So if we look a little bit at how this table is constructed, we could see here that there are 7 horizontal areas on this periodic table, and these are called periods. So the periodic table has 7 periods. If you also notice that along the vertical areas, we have 18 groups. And groups are organized for similar chemical properties to be grouped together. This is what Mendeleev believed, that he had his best organization system going on by putting these into their proper vertical areas. And most of his elements in his original chart lined up very well compared to our new modern periodic table. There are some groups that you guys should know the names of. Group number 1 are called alkali metals. These are very soft reactive metals. Group number 2 are called alkaline earth metals. Group number 16 are called chalcogens. This is the one with oxygen at the top of the group. Group number 17 are the halogens. These are very reactive, typical gases, though there is a liquid and a solid here. And then the last group are called noble gases. These are very unreactive gases that have a full octet of electrons. So this idea of a periodic table comes from the word periodicity. And in science, period means something that repeats over and over per given unit time. And if we can see that the elements on this table are very repetitive in terms of their properties. As soon as we have a non-reactive noble gas, the following element that comes after that non-reactive noble gas is a very reactive soft metal, an alkali metal. So we can see that these properties repeat periodically, which is why we call this the periodic table. So now let's look at the different types of elements we have on the periodic table. If we look at the periodic table, most of the elements that we know and have discovered are metals. And the metals are mainly found on the left side and in the central part of the periodic table, and they're going to have typical metallic properties that you guys know of. They're very shiny, they're very lustrous, they conduct electricity and heat, as well as they're ductile, and ductility means you can pull it out into a wire. So all of our wiring in this building and maybe in your household has due to that ductility of this metal. And they're also malleable, which means we can form them into shapes or pound them into sheets. The only element that's on the left side of the table that is not a metal is hydrogen. And hydrogen kind of sits on its own at the top of group 1, but we could easily move this over to group 17 as well. And hydrogen is just a very unique element, and it's got the simplest nucleus. So this, you got to remember that this is not a metal. All of the metals are typically solid at room temperature with the exception of one, and that's mercury, symbol Hg. So now let's talk about the nonmetals. Nonmetals, except for hydrogen, which we already discussed, are located on the right side of the periodic table, typically in the right upper right area. And here we're going to have all of our nonmetals. Our nonmetals are going to be very colorful or dull. So if we're talking about solid sulfur is this bright yellow. Chlorine gas is this pale green gas. Iodine is like a purplish color. As well as all of these will exist at different phases. All the noble gases are going to be gases. Of the halogens, we have some that are gases, one that's a liquid, which is bromine. So that's the only other liquid on the periodic table besides mercury is bromine. And as well as we have some solids in the halogens like iodine. Carbon's a solid, phosphorus is a solid. So these nonmetals encompass all phases. These are also not conductive. So the term we use for this is an insulator. So we use nonmetals typically as insulator. The last category is on the staircase area of the periodic table, which is located in the P block on the right side of the periodic table. And if you see the staircase, everything that's touching the flat part of the staircase is typically a metalloid. And a metalloid has properties of both metals and nonmetals. So it's very versatile, and we use these a lot in computer systems as semiconductors. So let's start talking about what we can do with these symbols from the periodic table. What we typically do with these things are create what are called chemical formulas. And a chemical formula is just using its elemental symbology to write how many of each of these different atoms we have within a compound. So we use the chemical symbol from the periodic table, and then we use this area underneath called the subscript. The subscript is going to denote how many of each atom that you have, and the subscript value comes after the symbol. So whatever digit comes after the symbol, that's going to be corresponding to the symbol before that subscript. So we can have all different kinds of formulas. We have empirical formula. An empirical formula is the easiest, most simplest way that we can write something, whether it be carbon dioxide, carbon monoxide. These are all empirical formulas because we can't divide by a common value to reduce this. If we have something like C2H4, these can both be divided by 2, so the empirical formula of this would be CH2. So that leads us to what is a molecular formula. So our compound like C2H4, that would be its molecular formula, and that's showing the exact number of how many atoms we have within that compound. The next higher order up that we could see of this are called our structural formulas, and our structural formulas show us how all the atoms are actually bonded together. So you can see all the connections between each of these different elements and atoms within the compound. The highest order we can get are called perspective drawings, and we use dash wedges to show coming out of the paper, coming into the paper. So we can start to visualize this as a three-dimensional object, even though we're writing on a two-dimensional surface. The other thing that you can do with a computer system is make computer models or space-filling models of these different perspective drawings. So now let's talk about molecules and molecular formulas. There's one thing that we should know first about molecules. Molecules are typically reserved for nonmetals. So if somebody's using the word molecule, they're most likely going to be talking about molecular compounds, which are composed of only nonmetals. Another vocabulary word I want you guys to know is what's an allotrope. An allotrope is the most common stable form, how you find an element. And there are a lot of elements on the periodic table that are nonmetals that exist as diatomic molecules. That's the allotropic form of how you would find this. Hydrogen is diatomic. The rest of these can be found like an upside down L on the periodic table, starting with nitrogen. So you've got N2, O2, fluorine, and then everything down the halogen group. So F2, Cl2, Br2, I2. These are all diatomic compounds, molecular compounds that are in their allotropic form. So now let's see how we actually write compounds and formulas out, as well as the four major naming systems. I would say you're going to need to put in a bit of memorization to understand these different naming systems, and there's four primary naming systems that we're going to cover in this video. The first of which is going to be called Ionic naming. So what you're going to need to do is start to memorize these very common ions. You could Google a common ion worksheet, or you could find it in a common textbook, but you're going to have what are called cations. Cations are any ions that have been positively charged, as well as you're going to have a list of anions, and anions are ions that are negatively charged. You have monoatomic cations and anions, which means you're going to have one single atom that's been ionized, as well as you're going to have polyatomic cations and anions, which means you have a whole unit or whole structure, and that whole structure is going to have an overall charge on it, even though it's considered one object. So something like ammonium NH4+ has one structure, but it's got an overall +1 charge. So here's a table that's got some common ionization states, and we could see that these are all monoatomic cations and anions. Typically metals lose electron, so metals typically form cations. So you could see all of the things, all of the different elements on the left side of the table, they ionize to positive charge. Nonmetals ionize to anions. They typically gain electrons. They love to rip electrons from other objects, so they ionize as to a negative charge. So for monoatomic ions, there's a pattern. Group 1 typically ionizes to +1. Group 2 typically ionizes to +2. Aluminum is +3. And then the nonmetals are a reverse, starting with the nitrogen group that ionizes to -3. The chalcogens ionize to -2, the one with the oxygen at the top of the group, and halogens typically ionize to -1. Everything's trying to reach noble gas configuration, which is an octet, and that's going to make the element as happy as possible. There are several exceptions to the octet, and we'll cover those in future videos. So now let's begin to make an ionic compound. It's very easy when you go to do this. You're going to need a cation. If we have something like sodium is +1 charge, and you're going to need an anion, something like chloride ion, which is -1 charge. The ratio of this would be a +1 to a -1 ion, so that when they chemically bond together, they make a neutral compound, sodium chloride. So the ratio here would be very easy, 1-to-1 for those charges to cancel out. If we have something with a higher charge like calcium, this +2, if it were going to form a compound with chloride ion, you would need 2 of those -1 chloride ions to cancel out the +2 charge of calcium. So calcium chloride is CaCl2. So what you're trying to do here is cancel out the charges. The easiest way to do that is to just take the charge and then bring it down diagonally to the opposite element, and that becomes the subscript of the opposite charged element. If it's a 2-to-2, we just reduce this as 1-to-1, showing our empirical formula. All ionic compounds are reported as empirical formulas. The next tricky part we need to talk about with ionic compounds is when we're dealing with metals from the D block that have multiple ionization states that are possible. Group 1 is always +1, group 2 is always +2, but when we get to the D block, stuff like copper and iron, these can have multiple charge states, so we need to tell the reader this. Iron could be iron 2 or iron 3. Which means it would have a +2 or a +3 charge respectively. And the way that we tell the reader that it's an iron 2 ion or an iron 3 ion is we use a Roman numeral. So there's no such thing as iron chloride. There's iron 2 chloride and iron 3 chloride. So you're going to have to put in work memorizing these different common ionization states of D block elements for you to be able to easily name ionic compounds. So let's see how we name an ionic compound. The first thing you're going to do is write the name of the cation. This should basically just be the element's name, with the exception of one polyatomic cation I want you guys to know, and I already mentioned it, it's ammonium, NH4+. All the other cations for general chemistry, AP chemistry that you come across are typically going to be metals. So if you see a metal in the front of the compound's name, it's going to be an ionic compound. So you're just going to write the name of the metal. In the case of sodium chloride, the name of the metal is sodium. The next thing you're going to do is use the root of the anion. So chlorine, the root of it is chlor. And then what we're going to do is change the ending of "ine" to "ide." So all of the ionic compounds, if they're monoatomic anions, are going to end with "ide." So we could see that sodium, chlor, ide. This is how we name an ionic compound. Let's look at a little more advanced one. If we have something like iron sulfate or iron 2 sulfate, what we're going to have to write down then is iron. You're going to write Roman numeral 2 in parentheses to show the reader that this is iron 2 ion. And then sulfate, which is SO4 minus 2, is going to be in a 1-to-1 ratio. So if you've got a polyatomic oxy anion, and that's going to be an anion that's got some electronegative element surrounded by oxygen atoms, the two possible endings that you could have are "ate" and "ite." So the way that we tell the difference between these oxy anions is it's going to have a family. So if we looked at something like chlorine and it's in its oxy anion state, it could be chlorine with one oxygen attached with a -1 charge. That's called hypochlorite. You could have ClO2 minus, that's called chlorite, ClO3 minus, that's called chlorate, and ClO4 minus is called perchlorate. So when you have less oxygen, the ending is going to be "ite," and when you have more oxygen, the ending is going to be "ate." If you have a family of 4, then you need to use your prefix hypo for the one with the least oxygen, and per for the one with the most oxygen. So again, we have hypochlorite, chlorite, chlorate, and perchlorate. Now let's move on to talk about acids. There are 2 major categories of acids, but before you get to name acids, I suggest you learn how to name ionic compounds, because those oxy anions are going to help us learn how to name oxy acids. So if you haven't had a good memorization yet of those oxy anions, it's going to be a struggle to name oxy acids. So the first category of acids are called binary acids, and binary means there's going to have 2 of something. There's going to be 2 elements to form a binary acid. Acids typically give hydrogen ions or protons. So if you see a compound that begins with hydrogen, most likely it's going to be an acid. So for a binary acid, it's going to have hydrogen with some other electronegative element attached to it. And the way that we name binary acids is we use the prefix hydro. You can only use the prefix hydro for binary acid. So something like this, HCl, this would be called hydrochloric acid. So the way we would name this is you'd use prefix hydro, you would use the root of the anion, so in this case it's chloride, so we would use the prefix chlor, and then we change "ide" to "ic," and then add acid. So hydrochloric acid. A lot of the halogens are primarily binary acids. So hydrofluoric, hydrobromic, hydroiodic, these are the common binary acids that you'll come across. The next group of acids that we're going to talk about are called oxy acids, and these are going to be based off of your oxy anions. So again, you're going to have to memorize. What we would do here is we only change the ending. If the oxy anion ended with "ite," we change the ending to "os." If it ended with "ate," we change the ending to "ic." So if we're going back to the chlorine family, hypochlorite, if we gave it a hydrogen and made it an acid and got rid of that -1 charge on hypochlorite, it would become hypochlorous acid. Chlorite would become chlorous acid. Chlorate would become chloric acid, and perchlorate would become perchloric acid. So again, you're going to need to know your oxy anions to be able to change "ite" and "ate" to "us" and "ic," respectively. The third naming system that we're going to go over now is called molecular naming. And just like we discussed earlier in the video, this is going to be all nonmetals. So if you look at a compound and you see all nonmetals and it doesn't begin with a hydrogen, so it's not an acid, then you're going to have to use molecular naming. In AP Chemistry and Gen Chem, it's typically going to be binary molecular compounds that you're going to be asked to name. And this is very easy. If you took geometry, you're going to know a lot of these prefixes. So here's a table of the common prefixes up to 10 that we're going to need to know. We're going to use mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca as 1 through 10. So what you're going to do for naming a molecular binary compound is, again, you're going to write the name of the element, just like you did for ionic compounds. So if we have something like this compound, N2O4, this would be dinitrogen because we have 2 nitrogen. The only time you don't use prefix mono is on the first element if there's only one. So an example of this would be like carbon dioxide. We do not call this monocarbon dioxide. We leave prefix mono off for the first element. Going back to our other example, N2O4, this would be dinitrogen. Then you're going to use the prefix tetra. But if you're going to have vowels that clash, like tetra and then ox to begin oxygen, you're going to drop the vowel from the prefix. So this would be tetroxide. You're going to use the root of oxygen, and then you're going to change the ending to "ide." So his full name would be dinitrogen tetroxide. Again, we'd not use prefix mono on the first element, and we wouldn't use the vowel on the prefix of the second element. Let's look at one more example. We could have carbon monoxide. We don't call this monocarbon monoxide. No, this is carbon monoxide. We drop the O from the prefix to let it blend into the root of the second element here. The last naming system and piece of this video is going to be simple organic naming. If you pass this class and you go to an organic class, organic chemistry class, you're going to learn very long systematic IUPAC names of organic compounds, but we're just going to discuss a very basic naming system here, and that's going to be of alkanes. What an alkane is a carbon-based compound that all has single bonds and hydrogens attached to them. So they're very simple hydrocarbons, all with single bonds. So the way that we denote how many carbons are in the simple chain of these alkanes is we look to see how many carbons are connected to each other. The prefixes are very similar to molecular after 4 carbon length. But before that, we have a very special organic system. A 1 carbon chain, we use prefix meth. For 2, we use eth. For 3 carbons is prop, and 4 carbons is bute. Anything after that is going to be using the molecular system, pent, hex, hept, oct, non, and dec. Since these are alkanes, they're going to end with ane. So this simple hydrocarbon would be called methane. This one would be called ethane. This one is propane. And this one is butane. We're going to learn one other decoration as well. And if you had an alkane, but you substituted one of the hydrogens for what's called an alcohol group, an OH group or hydroxyl group on this chain, then it's no longer an alkane, it would be called alcohol. So this would be methanol, and this one would be called ethanol. So there it is, guys. There's the video on the structure of the periodic table as well as naming systems. So if you enjoyed this video, if you liked it, send it to your favorite draft, send it to your imaginary friend, and we'll see you in the next video.